Okay, so these are the notes for section 2.6 on rational functions. So a rational function can be written in the form f of x equals n of x over d of x. N of x would be the numerator function, d of x is the denominator function. N of x and d of x are polynomials and cannot equal 0. If the numerator was equal to 0, then it would be 0 divided by something, which is always 0. And then if the denominator was 0, that would be something over 0, which is undefined. So they both have to be polynomial functions. There has to be something there other than 0. The domain of a rational function is whatever will make the denominator undefined or equal to 0. So we're always going to set our denominator equal to 0, and that's going to tell us what the domain cannot be. So for example, I've got f of x equals 2x plus 3 over x minus 4. So if I want to know what the domain of this function is, then I'm going to set the denominator equal to 0 and solve. So that means the domain can be all real numbers except x equals 4. If I plugged 4 into the denominator, 4 minus 4 would be 0, and so dividing by 0 is undefined. So any number except for 4 is part of the domain. Now we're going to look at the asymptotes of rational functions. First are vertical asymptotes. They are at the zeros of the denominator. So when you solve the denominator of a rational function, that tells you where the vertical asymptotes are going to be. That's also where the domain is not equal to those values. So for example, if I have f of x equals x squared plus x minus 2 over x squared minus x minus 6, then I'm going to factor the denominator or solve the denominator so that I can find out where the vertical asymptotes will be. So in this example, I factored the top and the bottom. The top factors into x plus 2 times x minus 1, and the bottom factors into x plus 2 times x minus 3. If anything cancels, like in this example, the x plus 2 cancels on the top and bottom, then we just ignore those for the asymptotes. That's actually where a hole in the graph would be. So this one, there is only going to be a vertical asymptote at when x minus 3 equals 0, or when x equals 3. Okay, that would be our vertical asymptote. That's also what the domain cannot equal. So any value except x equals 3 for the domain. Next is for horizontal asymptotes, and we have 3 different rules for horizontal asymptotes. If the highest exponent on the top is less than the highest exponent on the bottom, then the horizontal asymptote is y equals 0. So here's what that looks like. If I have x plus 1 on the top and x squared minus 4, I'm looking at the highest exponent on the top, which would be first, the first power, and the squared on the bottom. So the top is less than the bottom, so that means that this has a horizontal asymptote at y equals 0. Next, if the highest exponent on top is equal to the highest exponent on the bottom, if they have the same exponent, then you're going to take the leading coefficient on the top divided by the leading coefficient on the bottom. So an example might look like 2x squared plus 1 over x squared minus 4. So the x squareds are the same, so we're going to look at the coefficients of those x squareds. In this case, it would be 2 divided by 1. So 2 divided by 1 is just 2, so our horizontal asymptote for this example would be at y equals 2. And then last, if the highest exponent on top is greater than the highest exponent on the bottom, there is no horizontal asymptote. So that might look like this: 2x squared plus 1 over x minus 4. The top is squared and the bottom is to the first power, so that means there's no horizontal asymptote. But when there is no horizontal asymptote, there could be what's called a slant asymptote. So anytime you get no horizontal asymptote, then you definitely have to check for a slant asymptote. If there was a horizontal asymptote at either 0 or some other number, you don't need to worry about a slant asymptote. So for slant asymptotes, it's when the exponent on the top is exactly 1 greater than the one on the bottom. So something like this, x squared minus x over x plus 1, has to be exactly 1 greater than the bottom. So to find out the slant asymptote, we're going to have to do long division. This doesn't work for synthetic division. You need to do long division to do this. So long division will tell us what the linear function is that results in the slant asymptote. So for example, if I use my long division and actually work this out, I didn't show the work here, but if I divided x squared minus x by x plus 1, the answer would be x minus 2. And then there might be some remainder. We don't need to know what the remainder is for this situation. We're just looking at this term, the x minus 2. That's the equation of the slant asymptote, y equals x minus 2. Okay, so those are all the different types of asymptotes for rational functions. So what we're going to do is I'm going to show you how I find all the asymptotes, x and y intercepts for rational functions, and what I expect you to do for each problem when you're graphing these. So you need to leave some space above and below your equation. We're going to divide my paper or my section of paper into 4 equal pieces. So this could be like half of your paper or a quarter of the paper, depending on how big you write. But we need kind of 4 squares, and your equation is on the left-hand side, split in between the 2 squares on that side. So I've got x squared minus 5x plus 4 over x squared minus 4. In each of these squares, we're going to do a little part of the puzzle that's going to tell us about the graph of this rational function. Then we're going to take those pieces and put them on the graph. So first off, in the upper left-hand corner, we're going to look at horizontal or slant asymptotes. Okay, so first we're going to check for horizontal asymptotes. If it doesn't have a horizontal asymptote, then it's possible that it has a slant. So when you're checking for horizontal asymptotes, you're just comparing those leading two coefficients. And you want to see, are the exponents equal? Is the top bigger than the bottom? Is the bottom bigger than the top? What's going on here? We had those 3 rules we just talked about. Well, in this case, they're the same. So when the exponents on the top and bottom are the same, you're going to take the leading coefficients for the horizontal asymptote. So that's going to be y equals x squared over x squared, which is 1 over 1. So y equals 1 is our horizontal asymptote for this problem. Now we're going to go in the bottom left hand, and we're going to look at y-intercepts. Y-intercepts are when x equals 0 in the problem. And it works out that if you just look at those constant terms on the top and the bottom and you divide those out, that will give you where the y-intercepts are. So in this case, 4 divided by negative 4 is y equals negative 1. So that's where our y-intercept will be, 0, negative 1. Okay, now we're going to go to the right-hand side of our squares, and we're going to factor the top and factor the bottom. Okay, so when I factor the top, this is going to factor into x minus 4 times x minus 1. And then the bottom is a difference of 2 squares, which is x minus 2 times x plus 2. So when we look at the top, this is going to give us our x-intercepts, or when y equals 0. So you're going to take your top 2 factors, and you're going to set each of those equal to 0. X minus 4 equals 0, and x minus 1 equals 0. And then you can solve. So x equals 4 and x equals 1 are your x-intercepts. The bottom 2 factors are going to tell you about your vertical asymptotes. So you're going to set these 2 factors equal to 0, and that will tell you where your vertical asymptotes are. So x minus 2 equals 0, x plus 2 equals 0. Our vertical asymptotes are going to be at 2 and negative 2. So now what I'm going to do is I'm going to take all these pieces and I'm going to use these to help me draw the picture of this rational function. So on my graph paper, I've got my equation down here so I can remember what it is. And then I've just written out all the different things that I found to help me remember as I'm plotting these. So I'm going to start with my horizontal asymptote at y equals 1. So remember, when we're drawing asymptotes, we're going to draw a dotted line. My vertical asymptotes were at 2 and negative 2. So these asymptotes are guides for our function. They're never going to cross these, or there's certain places that they won't cross. And they're kind of be bound between different sections here. So let's plot our points. y equals -1 was our y-intercept. X equals 4 and x equals 1 is our x-intercepts. Okay, so right now, just based on those things, this isn't a great picture of what's going on. So I would then use my calculator or plug in a few more values to help me plot these points. So I just picked a few values for x and plugged them in to see what they would equal. So I started at -10 and plugged in -10, and it was a little more than 1.5. Then I plugged in -5, and it was close to 3.5. I plugged in -4, and it was closer to 7. So you can see on this part of the graph, it's going to be bound between those two pieces of the asymptote. Okay, in between, I want to pick some numbers in here to see what's happening. So if I pick -3, it's going to be about -3.5. And then when I picked like 1.5, it was almost to 2. So I just wanted to see what's it doing in between that last point and the asymptote. So it's going to be bound between those two vertical asymptotes. And then on the right section, if I plug in positive 2.5, it's about -1. So I just picked a couple of points in here so I could kind of figure out what's going on. And then when you connect the dots, you're just trying to draw a curve that would go in between each of those. Okay? So this is just an idea of what it looks like. You want to have all of your pieces labeled, your asymptotes and your intercepts. And then if you throw a few more points on there, that's good. So let's look at how to type this into the calculator. So when you go to y equals and you type this in, make sure that you put the numerator in parentheses and the denominator in parentheses. And you can go back to the original problem. And then when you hit graph, it's going to look something like this. Now some of your calculators, if you remember, it looks like it draws in the asymptotes, but really it's just connecting the top of the graph to the bottom of the graph because it doesn't understand that they don't connect. Those asymptotes are really imaginary lines or guides on the graph. Okay, so for each of these problems, you're going to draw the box with all the different parts and pieces and then label those on the graph as well.